Am I audible?
Yes.
Thank you. Good evening, one and all present. Today's session is on the topic the Atal Tunnel Uniqueness and Construction Challenges. We'll begin shortly. Before that, let me brief in some general instructions for the participants. All participants are requested to mute their microphones and switch off your cameras during the entire session. All your doubts and queries can be cleared at the end of the session. Please make use of your chat box or unmute yourself for the same. At the end of the session, a feedback form shall be circulated in your WhatsApp group and here in the chat box. Please do fill in without fail as your certificates are issued on that basis. So, as I mentioned earlier, today's session is on the topic the Atal Tunnel Uniqueness and Construction Challenges handled by E.R. Sunil Vasudevan, who is the PMC of Atal Tunnel Project, a techno-legal expert and former CEO of D2 Consult Australia, and will be chaired by Dr. K. Balan, President of IGS Trivandrum Chapter. He is a postgraduate in geotechnical engineering from University of Kerala and has specialized in subsoil investigation and design. He has designed and executed several projects using natural geotextiles. Currently, he is the Vice President of Rajdhani Institutes of Science and Technology, Trivandrum. And this session will be co-chaired by Tinu Krishna S., Vice President of IGS Student Chapter, Marine Engineering College. We are very honored to have you, Balan sir. On behalf of the whole IGS Student Chapter, I welcome you to lead this session. Sir, now the session is all yours.
Good evening and thank you. Dear dignitaries,
Good evening, sir.
Rani, Narayan sir, and others, delegates. It is a great pleasure to have Sunil Vasudevan as the keynote speaker today. And luckily, he was my senior during my BTech time, and during we had our masters in CET almost contemporary time. Myself was in geotech, and Sunil Vasudevan sir was in transportation engineering. He was working in state PWD, as especially in highway, and he is better known as a techno-legal expert. He has not only the academic qualifications in engineering, but also he is an LL graduate. and also MA in Business Economics, Business Administration, Environmental Management. So, and so the engineer means he will have a professional membership. So membership. Sunil Vasudevan sir is having membership in American Society of Civil Engineers, fellow of Institution of Engineers, is member in Indian Road Congress, Indian Institute of Arbitrators and Mediators, then fellow of Indian Institute of Technical Arbitrators, and Bar Council of Kerala is a member, empaneled as arbitrator in Honorable High Court of Kerala, and so on. So to summarize his expertise, is he has got about 42 years of experience in the diverse field of infrastructure, has headed and handled a wide range of complex projects under turnkey, BOT, and EPC in India and abroad under National Highway Authority of India, NHIDL, NHIDCL, Ministry of Defense, and state governments under World Bank or Asian Development Bank funding, operated under FIDIC conditions in position such as CEO, Director, and Corporate Vice President, Project Director, Chief Engineer. He has abundant professional experience in different capacities in the area of arbitration and dispute resolution, contractual legal, contract management, contract administration, and procurement of contracts, project appraisal, evaluation and technical audit, performance-based contract development and management, asset management, etc., etc. So he has got an experience not only in the government service, especially in PWD, but also he worked various positions in abroad, in highway and other technical manager in gas international, Sharjah, etc., etc. Such a versatile person we have, and he will share his experience on the Atal Tunnel, which we had Prime Minister inaugurated recently, and the similar prestigious project is going to come in Kerala in Wayanad again, and the tunnel. So his experience on this particular project will enlighten not only the students but also the IGS members of Trivandrum chapter. And I welcome Sunil Vasudevan sir to deliver the lecture. Thank you, sir. Please.
Am I audible to you?
Yes, sir. Please.
Okay. So first of all, let me thank Dr. Balan very much for his flattering words about me. I'm nothing so special, just a humble human being. So, what he said is right. I was in PWD and retired as Deputy Chief Engineer, but the Kerala government has got a facility of taking leave and to work in private sector in India or abroad. So I took leave for a total of around half of my service period, about 18 to 19 years, and different periods. And what got I was lucky enough to work in international consultant companies. So as a part of that, lastly, just before retirement, for 6 years, I was the CEO of this D2 Consults of Austria, who were the project management consultants for the Rohtang Tunnel. Okay, the name of the tunnel was then Rohtang, and now it is renamed as Atal Tunnel. So in my lecture, I may either say Rohtang Tunnel or Atal Tunnel, but both are same. So once again, I thank very much. Let me. Is it okay? Let me begin my presentation. It's okay. I'll share my screen. It's okay. I hope I have a go ahead to share my start my presentation.
Yes, sir. You have made a presenter, sir. You can go ahead.
Okay, thank you. Okay, let me tell you a few words about this. Uh, See, this is today's talk because I was told that a lot of students are also attending, so my lecture will be not very technical. So what I am going to share with you is my practical experience while constructing the Atal Tunnel. So as I told you earlier, D2 Consults of Austria was the project management consultants for the Atal Tunnel, and they are one of the pioneers in this NATM technology. Atal Tunnel was constructed using NATM technology, which is a type of drill and blast technology. So it's MD at that time when I was with them. Dr. Alfred Schulter actually developed the modern type of NATM technology. NATM technology was there earlier, but he refined it. So he was also considered as one of the pioneers in the modern NATM technology for tunneling. So I was very lucky to work with a consultant firm whose MD himself was a pioneer in this technology. So in this talk, I will avoid this complex engineering or technical jargons or rock mechanics or soil mechanics. I will use them only when absolutely necessary. So it will be, talk will be very simple so that students and young engineers can understand it. I hope the experts and veterans in geotechnical field will excuse me. So I'll also try to show a few videos and photographs so that the participants would get a feel of what we have done there. And moreover, what I think is that we engineers are born visualizers. We visualize everything in our life, not just by reading it. So a visual presentation would be going deep into our mind, and you'll remember that always, just like watching a movie or whatever it may be. So I hope you would enjoy the presentation. Let's begin this with a video, just as an introductory video. Here we go. I hope you can all see the video.
Yes, sir.
Okay, there is no sound for the first few seconds. It's a kind of a 3-minute, 45-second video produced by the contractors of the Rohtang Tunnel. One of the contractors, of course. Something went wrong with the video, I'm sorry. We come back to the hope you got an idea about the Rohtang Tunnel, where it is and how the construction was carried out. Now let's move on. See, this gives some key factors about the Rohtang Tunnel. Much of this are just for academic interest. When I share this video, PowerPoint presentation with you, you can go through that later. But the most important things which we need to know about is the maximum overburden of the tunnel was 1,908 meters. And the construction method was NATM method. NATM means New Austrian Tunneling Method. It's a different kind, it's a kind of drill and blast way. The other things are elevation, Rohtang project course length and all are just for, statistics. So the one thing is that the cost is mentioned as 3,200 crore, which includes the cost of different consultancies and all the expenses included. The actual construction contract was originally given for around 1,500 crores, which was later increased due to a problem we encountered in Serinala location due to a fault zone there. So the contract was revised. So that was the actual construction cost. See, this picture shows the finished tunnel. You might have seen this in videos, or it's available in the public platform. The Prime Minister has inaugurated it. This is the first entry. This is what I think you might have noticed about mentioning about snow galleries in the video. This is a snow gallery which is constructed just before the entrance of the south portal. That is the south portal before the entrance to prevent the snow from covering it or blocking it. So you can see that it comes like this and takes a sharp right turn and goes inside. This is what you see inside now. So in the small figure also you can see that the road comes here and takes a sharp right turn and goes across under the mountain. This relief map gives you an idea about a 3D idea about what we have just seen in the video. This is Manali town, and from there about 14 kilometers up we have the tunnel started. This place is called Palchan, from where the present road is. From there you take right turn and go winding up, go down. This is the Rohtang Pass, the topmost portion. Then go down to the other side and go like this to Leh. So that is the route. So to cover this distance from Palchan to this side, Gampu, it's a very tough terrain. You might have seen in the videos, the trucks are slipping and muddy and everything, landslides. And for 6 months, the road is closed. So that is what prompted the government to think about a tunnel going under the mountain. And that makes it an all-weather road. So this road deviates, the entrance or approach road to the tunnel deviates from Palchan to the left, and this goes. On the way, just a few kilometers before this, there is a tourist spot where you can enjoy the snow. It is called Solang Valley. It's a big tourist spot. Anybody who has gone to visited Manali would definitely might have gone to Solang Valley. So the entrance to the tunnel, the road to the tunnel goes through the Solang Valley, and this is the tunnel. So let's just have an overview of this, why this tunnel was made. So, this is in the Leh-Manali highway, which is number 3, which is socially, strategically, and when you look at the national defense perspective, it is very important. This is crossing the Pir Panchal ranges. The ranges of Himalayas we cross here is called Pir Panchal. Earlier, it used to take 5 hours to cross this 46 kilometers, but now you can just zip through in 10 to 15 minutes. So that is the benefit of it. It is not only beneficial for the general public, it's also very important for our defense purpose. So this tunnel is strategically and defense-wise also very important. So the idea mooted in 1960 itself, Jawaharlal Nehru initially thought about this. See, when the Jawahar Tunnel from Jammu to Kashmir was made, even at that time, This also was considered. Even Geological Survey and many other agencies surveyed this, prepared basic feasibility reports and all those things. And again, it was given to the RISE for a feasibility report. But in 2000, our then Prime Minister, Mr. Atal Bihari Vajpayee, decided that we cannot wait for studying and we cannot wait on it. We cannot sit on it. We need to do it very quickly. So he set up a special project for this under the Border Routes Organization with a chief engineer to head this. So based on that, his decision, the feasibility studies were updated again in 2013. So the final feasibility study and the DPR for the tunnel was provided, and then this was done by SMEC of New Zealand, and then this has gone to bid, and the contract is Strabag Afghans JV. Strabag is a German contractor. They have done hundreds of tunnels in the Alps. Alps is something so climatically it is more or less similar to Himalayas, the tunnels region where they have built the tunnels in the snow and very tough conditions, except the geology. Geology is a little bit different, not little bit, but different. So the SMEC were the design consultants, and also they were appointed as the advisory consultants during construction. The project, as I told earlier, the project management consultancy was entrusted with the D2 Consults. I was the CEO of D2 Consults with my office in Delhi. So the construction started in 2010 June with the first blast. Our the then Defense Minister, Mr. A.K. Antony, along with Mrs. Sonia Gandhi, was present for the function. This is another location map. You might have got a very better view when you watch the video and then the relief map. See, this is the location of the South Portal. This is where we have seen our Prime Minister inaugurated. This was like this before we started constructing the tunnel. So this yellow dot shows the exact location of the South Portal. Then first thing what we did was this rock was blasted and a covering and an entrance gate was made that is called the portal. This is the first step in tunneling. Then after the portal is constructed, then the actual tunnel alignment or tunnel starts from that point. And this picture shows the first blasting of the face of the tunnel. Similarly, on the other side, the northern side, this is where we have seen the North Portal right now. Not many pictures of the North Portal has come in the media. What you are seeing here in the North Portal as the twin tunnel, which has come in the media, that is not the correct one. This is, I'd say this one. This one is not correct. This is not of the Rohtang Tunnel or Atal Tunnel. This is actually the photograph of a twin tunnel in United States in California. It is called Devil's Slide Bypass Tunnels. Somebody in the media has published it as the North Portal of Rohtang Tunnel, and everybody got carried away with that. So don't think that this is the North Portal. North Portal, it's a single tube tunnel. This is the North Portal exit entry. The right side where you can see the truck line. So the earlier slide we have seen this South Portal, that is on the Manali side. This is the North Portal on the Leh side. Now let's go a little bit technical. This is the cross section of the tunnel, Atal Tunnel. This is a horseshoe-shaped tunnel. It's not circular or elliptical or anything. It's a horseshoe with 10.4 meter height and a width of 11.25 meters. The road width is 10.4 meters with median and about 3.74 meter carriageway on either sides with 1 meter footpath each. So it's a single tube dual carriageway tunnel. Then we have the ventilation system, electrical system, and all other safety systems and everything at the sides. We have drainage system on both sides below it, and right at the center below it, there is a small tunnel, which is about 2.25 meter height, which is good enough for a reasonably high human being can walk through. This can be used as an escape tunnel. So in the event of fire or mishap or anything, there are escape routes built into the sides of the tunnel at every 200 meters. So there is a way you can go down and come into this and escape out from the tunnel. This is also ventilation provision is also given in this tunnel. So this is the longitudinal section of the mountain where we have built the tunnel. It starts from the left side. That is the this is the south portal, and this is the north portal. This is the tunnel. So what you see here, you would understand how much overburden is over this. It's a huge. This maximum overburden is 1,980 meters at this point, which means almost 2 kilometers of mountain stands above the tunnel at this portion, which is not very common in tunnels, only in some tunnels, not all the tunnels. And also the geology is very treachery. We cannot predict what's going to happen when. So that is one of the major challenges. So these are also some technical matters, which is just for academic purpose or statistics purpose. The maximum overburden is this. I have included this. If anyone of you want to refer to this at a later time, you will get some statistics. So let's talk about the challenges, what we faced. One is high altitude. Okay, we can tackle it, no problem. Inclement weather, we can tackle it to a certain extent because it's either snowy or rainy. I don't think there is even a single day without a rain or snow. It's always wet there. And the speciality of this location is the Manali, Himachal, and the Himalayan region is that the weather changes any moment. Because one time of 9 o'clock, you'll see a good sunny weather and shining like anything. Within 15 minutes, you'll see the clouds gathering up in the sky and either a snowfall or a rain is coming. So it's most unpredictable weather conditions there. So we have to be ready for everything. And heavy snowfall is another thing. Winter starts from mid of October or November and then continues up to mid of April. So these 6 or 7 months, it's severe winter, and December, January, February, it's horrible. I'll show you some photographs later during this presentation, so you'll get a feel of what the Manali area looks in winter. Then another one is that the area is prone for avalanches and landslides. It's because of the geology and the climate both. Right from this approach road to the tunnel, from Palchan to the south portal, we have about 20 locations of avalanche and landslide locations. So even during constructions, we had a lot of problem. We don't know, one morning there will be avalanche, and then we'll have to clear it. But there is weather prediction system there, and there is an Institute of Avalanche Prediction and Research Center in Manali town. Closely watches the weather and gives advance warning to us, the possibility of a landslide or avalanche, then we will take the precautions. But when the tunnel is open, we cannot simply rely on that one, or you cannot simply close it down at short notice, close the road at short notice. So what we have done is that we have constructed snow galleries and avalanche protective structures along this road at all these places, so that even if an avalanche or landslide comes up, it goes over the top of this. It's a kind of box-like structure, just like an underpass. So whatever is coming down the hill flows over this, very strong structures. Then the accessibility, of course, hilly area, the accessibility is different. Then the most troublesome challenge of the geology, and among geology, other geological issues, the fault zone we found under the Seri Nalla. Seri Nalla is a rivulet. So it's a Hindi word. So Seri Nalla. So under this small stream, we had to cross the tunnel under this, and there was a fault zone just above that. So that is where we encountered the biggest problem in this tunnel construction. The construction, we lost about 5 years just because of this. So they say initially the progress was good. We used to progress about 1 or 2 meters, even 5-10 meters is an average about 1 to 2 meters. Even 5 or 10 meters progress was achieved in the initial stages. But by 2012, when we moved into the tunnel to about 2,300, about 2.5 kilometers, 2,300 meters chain. I think it is chain through 2342 or 2312, something like that. So about 2.5 kilometers from the south portal, moved in. Suddenly, one day after a blast, there was a big flow of mud, water, and everything. So nobody was injured, or nobody, there's no casualty. But from that day onwards, the progress was almost nil for some time. We couldn't even move an inch. Then we tried a lot of modern technical methods, consulted a lot of people worldwide, experts, internal, and all those things, and geologists, everybody. And then slowly we resumed the construction, and the progress was literally inch by inch, where we used to blast and go 5 or 10 meters a day. Now it is about half a meter or quarter a meter, something like that. Anyway, I'll discuss about it later. So as I said earlier, one of the problem was the heavy snowfall. So there were many occasions when the staff had to be evacuated by helicopter because they get caught. The road, because of an avalanche or a snowfall, the road is closed and the workers or officers or staff get caught on the other side. So we had to get the help of helicopters. So this is something which I told you earlier, the avalanche and landslide prone locations where we have built snow galleries now. As I told you, one of the snow galleries is right in front of the south portal, just behind this gate, which you can see on the top left corner of this presentation. Just behind this, the snow gallery is there. Through that, we go this way and then turn right into the tunnel. This would give, I'll show you some pictures of the winter season there. This would give you some idea about how we were living or going through this winter season at that in Manali. So the left side is our office and the office of the chief engineer and the officers of the border security force. Actually, this is the office room of the chief engineer. On the right side, you can see this snow, which is lying on the roof, is just one night's snowfall. It is not accumulated through days, just one night. Yesterday it was clean, and today you could see this much, more than a meter high snow. So this is the condition there. This is another view. You can see on the left side, this is myself standing there. And on the right side, that's our MD, Dr. Alfred Schulter. I told you that he is one of the pioneers, can be considered as the founder of the modern atom technology. This is how the Manali town looks. The earlier pictures I showed you was our office, which is around 14 kilometers from Manali town and about 1,000 meters above Manali town. This is Manali town. This is how the people of the Manali town live in winter. Just to give an idea about it. If anybody wants to visit or see snow, they should visit during winter. This is the entrance to South Portal during winter. This is where Prime Minister inaugurated. Now you would have seen a very, very beautiful portal and all those things there. This is the picture of the South Portal in a winter season. This is what I told you about snow gallery. This is called snow gallery. So all the landslides, any avalanches or anything will be protected, and everything will be flowing over this, and the road goes under it. So we have built so many snow galleries like this. Let's view a couple of videos more. This is the road going to the tunnel, and now see the difference, how different it is inside the tunnel and outside in winter. Today video comes out of the tunnel in winter. I hope you got an idea about the winter there. See, inside the tunnel, it's very hot and humid, and we wear sweaters and everything, many layers of woolen clothes outside, and once we move into the tunnel, we start sweating. So we have to remove all these things. So this is the change. Now let's talk a little bit about the geology. I think yesterday also in a presentation, the expert has talked about the formation of the Himalayan mountain range, which is created as a result of the push of the Indian plate and Eurasian plate, the two tectonic plates. They say that it started about 50 million years ago and even continues today. 225 million ago, India was a large island near Australian coast. It moved into the Eurasian plate even and hit. So it's slowly pushing to the China side, and then the bulge forms. The bulge that formed is the Himalayas. It's called as one of the youngest mountains because it's still being grown, still in the maybe in the infancy. I don't know, infancy or whatever it may be, but it's still, the height is still increasing. That is what we could read in the public domain. The geology of this location consists of quartzites with schist, quartzite biotite sits within dense fillets. This is what forms the geology of the mountain in this area. So the characteristics are, it's a very complex because squeezing and swelling conditions is a big issue. Cavity formation within the rocks, and due to shattered and sheared rock, the ingress of water and the geothermal gradient is very high. It increases very steeply. So this is a geological mapping of the location. This is where you can see the tunnel from the south portal. This is the tunnel location. So we have sheared rock, filleted quartzite, fillets, all of these things in this location. So this will give you an idea about the geology. Now let's talk about the Serenal law. The present Serenal law, this is about 250, at this point, that is 2 plus 250, 2.25 kilometers inside. It is about 250 meters above the tunnel top. So what happens is, when the ground, I'll show you the cross section later, the ground under the Serenal, we have shattered in sheared rocks and gravels and everything, and water seeps through it. And a fault zone is formed, and the tunnel crosses through the fault zone. So at this point, from this Chinese 2 plus 250 onwards, the water from the stream above comes into the tunnel, carrying with a lot of mud, rock, and everything. So no life was lost, luckily. And the techniques we used was umbrella roofing, pipe roofing, advanced deep probing, forepoling, deep grouting, etc. I'll explain about this now. Umbrella roofing, as you said, it's an umbrella. It's a canopy-like structure which is built immediately after blasting to protect the location which is already blasted. So it will not, rocks and mud and small rock pieces and will not fall over the people working there until a proper support is given. And pipe roofing is another way of providing this temporary support. So with umbrella roofing and pipe roofing, what we do is that we push rods into this and make an umbrella or make a roof, so that these pipes, the gap between these pipes is only where there is unsupported area. So that if the unsupported area for this 11.4 meter wide tunnel, the total unsupported area, if nothing is given, is 11.4 meter. That much span of rock has to be supported. But when we drive in these pipes and umbrella, the unsupported width becomes less, about half a meter or 30 centimeter or 70 centimeter, whatever it may be. It depends on the design. So the unsupported width is reduced so that you get a general support. It's a temporary support. It's not a permanent support. It's just for the construction purpose. Anyway, but we leave it there. Then what we do is the advanced deep probing. We use drilling machines and drill deep into the face of the tunnel, behind the face of the tunnel, and see or understand what is behind it, the geology of the rock behind it, so that adequate precautions can be taken when the blasting is done. Forepoling is also that kind of thing. We dry poles in advance before blasting. So umbrella roofing and pipe roofing is done immediately after the blasting to protect this. But if the rock is very bad, then we do forepoling. The poles are pushed into the tunnel face, into the unblasted rock, further into it, so that when it is blasted, the roof will be there. Another treatment was done is that deep grouting. The rock, or even, you cannot call it rock. Sometimes it is just sand, soil, mud, and water and everything. So you divert the water, putting pipes, and then inject cement grout into it, pump the cement grout, allow it to dry, so that it becomes a whole mass. So that also is a safety measure. So the problem what we have seen is that the rock quality is very poor, as I told earlier. The highly fractured rock mass with the number of shear seams and shear failure. And the geological discontinuities, that has also caused a problem, that are parallel to the tunnel axis. So that means when we are driving like this, these discontinuities or faults are parallel to it. That is creating a lot of problem, because we have to take care of it all along the way. So this is the Serenal law. cross section. This is a photograph at the top taken during summer. This is the actual Serinalla. The tunnel is about 250 meters under this. So let's have a close. Let's have a close look at the Serinalla cross section. This is the Serinalla cross section. You can see that this is the small rivulet. These are all gravel kind water bearing zone. So right under this we have our tunnel here. Sorry. So we have our tunnel somewhere here. So all the water seeping through this gravel and everything enters the tunnel at this location. This was the problem we faced. So I'll show you a few cross sections in the tunnel where we met the fault zone. This is the first one, and when we move forward, this goes here, and when we further move, it moves out. This is how we encountered with this fault zone location. Show you another video. I think if you are getting bored, we can go for another video. This is a video taken when we were going for inspections. All the videos, other than the first one which I showed you, which is maybe AFCONS, and the last one which I will show you, is all taken by me. This is also taken by me when I was going inside the tunnel for an inspection. So you will get a feel of how we travel inside this tunnel and what's the ambience of it. Now let's discuss in a few words about two different tunneling methods. Maybe students may be interested, students who are interested in tunneling that subject may be interested in this. So basically we have two tunneling methods. One is a TBM method, which is done by a big machine called tunnel boring machine, that is TBM. So this is the big TBM machine. In front of it you will see the diamond base. This whole thing will rotate, and the whole thing is of the diameter of the tunnel. Suppose our tunnel is of a diameter of 12 meters. This is a 12 meter diameter tunnel. So think about the size of this. It's very huge, and each one is made specifically for a particular tunnel. We will not reuse it again. So this method is very costly. And then this is the drilling section, and behind it what you can see is that a lot of other things going behind this. That is, even this is drilled, and through this the muck comes out, trucks come inside, and muck is taken away by all the trucks fly inside this, goes out, and then other trucks bring in the linings, and this concrete linings are fixed as the last thing. So this is gradually, the whole thing gradually moves forward. So in the front there is pure rock which is ground by the drill bits. So the machine slowly moves, and the machine moves away. The tail of the machine leaves a finished tunnel behind. So when this machine moves from one end to the other end, the tunnel is completed. So this is basically worked by a tunnel boring machine. But this is very fast, but not suitable for the locations like Rohtang, where geology has got a problem. There are a lot of uncertainties. But when you are sure about the underground conditions. You have the time is essential or is a major element. You go for drill and blast. I mean TBM method. So this won't be so. There will not be any blast or sounds like that or vibrations like drill and blast method in tunnel boring machine. So that's a kind of safer method or a kind of environmental friendly method as you can call it. The second one is drill and blast method. Drill and blast is just what the English word says. You drill, put some explosives in it, blast it, remove the rock, carry it away, finish it, then move forward. So this is what you call by drill and blast. It's a conventional, very old method. So then, in usual drill and blast method, what we do is you drill, blast the approximate circumference of the tunnel. There will be overblasting, underblasting, and everything, which is all corrected by concrete later. And the unsupported rocks are then supported by well-designed reinforced concrete linings and other supports and everything. The load is taken by the support system and linings. So this is the drill and blast method. Now when you come to the new Austrian tunneling method, that is NATM, this is a particular type or special type or modified type of drill and blast. Here, the basic thing is, this is also called this, even though it is called the new Austrian tunneling method, there are other names or also for it, sequential excavation. What happened? Something popped up. Okay. Sequential excavation method or sprayed concrete lining method, like that. See, what is important in this event from the engineering viewpoint is that in the normal drill and blast method or TBM method, the load of the surface or rock mass is taken by the structures we built after drilling it, after making the hole. But here in NATM method, it utilizes the strength of the rock mass itself, like an arch. The arch supports by itself. You can just do a brick arch, just like the arch shape. That is what supporting the whole structure. So the rock itself takes care of the stresses. Whatever support we give is temporary supports and to prevent falling of rocks and loose materials. There is no structural support given in NATM method. So this is the peculiarity or speciality of the NATM method. So the important factor is that it's not only the arch, the ring has to close at the bottom also. So it has to form a ring. So the stresses are distributed like that and it's within that loop. So another thing is that when you define this NATM, it is a design as you go method. This means usually in tunneling, what we do is that you design in advance, every cross section, decide everything and just go. But here, there is no detailed design or the entire design is not done first. The tunnel alignment and design, typical designs based on the borehole logs, borehole details and the geological investigations and everything, they classify the rocks into different classes, 1, 2, 3, 4, 5, 6 like that. So in Rohtang, the earlier classification was 4 types of rocks. So for these 4 different types of rocks, you design typical cross sections. This is what the preliminary design or what you get in the DPL. Actual design is done at the site along with the construction. So that is why you call it as design as you go method. You design as you go. So how this is done? So what happens is that the geologist, the geotechnical expert, the tunnel engineer, The authority, the engineer, the client, and the contractor, the project managers or team leaders or the engineers of the client, all these, a team is formed, about 6, 7, 8 people of the contractor, the consultant, and the client. If the design consultant and construction supervision consultant, PMC consultant, and client. All the 3 or 4 people form a team, and this team of experts inspect the tunnel phase. They inspect this and generate an opinion about what kind of support should be given here at this place, the already excavated place, and what we should expect visible phase. So what we should expect after the next blast. This is what they decide. And immediately upon that, the next blast is done and the preparations for the protection is already done. So we move ahead like that. So this is designed as you go forward. This is the peculiarity of atom tunneling. So let me show you how it is documented. RES is the required excavation support system. This means this team of experts inspects and they decide what should be given as a supporting system after excavation. This form is filled up by this expert, signed by all the expert. It gives face of the supporting body, elephant foot, whether it is elephant footing, round length, what are all the things, rock, bolts and everything, short treat, ceiling and everything. So this is what is done by the experts. And after blasting, there will be a little bit change as per the actual conditions. Then they fill in another form, which is the actual tunnel support sheet. So this is also filled up and signed by all the parties. So this is a record for what they have decided to do and what they have done after this. The second one is a kind of as-built. So let's discuss about the sequence of methodology and sequence of atom tunneling. First is that as I said earlier, after drilling, after blasting, the rock mass takes the support in the form of an arc, and then to give full support for the section, it's a quick closure of the invert is essential. This is a very important factor in atom tunneling. So the invert means the bottom part of the tunnel. So you cannot wait for several days. Maybe within a few days, you will have to construct the bottom portion so that the entire ring is formed to take care of the loads. See, this is it. First we blast here and arc is coming on the top, and as early as possible you construct the bottom of it also so that the whole thing forms a ring and takes care of it, takes care of the load. So these are the 7 different elements which I have mentioned earlier. It utilizes the strength of the existing rock. Then this I will explain. Short treat with mesh, deformation monitoring, flexible support, invert closing, which we have discussed right now. Rock classification, that also we discussed. Then appropriate contract. Okay, utilizing the strength of this, that is relies on the inherent strength of the rock mass, which we had discussed earlier. The short treat protection is that immediately after blasting, we fix normal wire mesh. As you have seen in our homes or places where you put wire meshes, simple wire meshes. Maybe the wires are a little bit thicker. You fix it to the surface of the blasted surface, then concrete is pumped at high force through nozzles, which is called short treating, and it sticks onto this so that this wire mesh and concrete forms a kind of support to the roof. Remember, it's not a support for the entire rock mass above the tunnel. It is just a support to prevent falling of loose materials or cracked materials. These are all called temporary support. Then we put steel ribs or anchor bolts, a lot of other things depending on the type of rock we encounter to give temporary protection. After that, finally, when the ring is closed, everything is fine. That ring will take care of the entire rock mass over the tunnel. And another important element is that we have to measure and monitor the movement of the rock immediately after blasting. Definitely, we are making a big hole into the mountain. So when there is nothing there, the rock above this exerts force on this. It's due to its weight. There will be deformation. There will be strain due to the stress. So there will be, the rocks will adjust by themselves. So there will be a little bit of deformation or deflection in the rocks. This is permissible, but we have to monitor it. For that, we put 3D monitoring equipments. Different equipments are there. With these electronic equipments, we fix it and monitor it hour by hour or day by day for the next 24 or 48 hours. We can see very clearly that the deformation is very high in the beginning, and it slowly comes down and down and down and down, and minimal after about generally 24 hours. So when that is stable, we can say that it's stable. If it is not stable, we have to take other supportive measures. This is very important. The measuring, it's a three-dimensional, that is called 3D monitoring, X, Y, and Z axis. Then different supports which I have told earlier is a flexible supports. These supports, what we give is flexible support. You remember, just wire meshes and a little bit of concrete sprayed and rock bolts are all not very rigid. It's flexible. It allows the deformation or strain to a certain limit. So we have to allow for the deformation, and after some time the rock settles by itself. And closing of the invert is very important. Then only it forms the ring and takes the stress all around it. Correct rock mass classification is important from the geological point of view. If we wrongly classify it, you will encounter with all the problems. The last and seventh one is suitable contract, because the contractor is very much responsible during the construction, not like just ordinary contracts. So even in design or decision making, he has gotten a very, very important role. So the contract has to be framed to suit that. Now let's see the operation cycle. See, first, as we said, the team go and inspect the rock class. Then they take a decision on drill depth, number of drill holes, the location of the holes, and the explosive strength, that is blast charge strength. Then you drill it, blast it. Then after blasting, everybody will come out during the blasting. Then after the smoke and dust settles, people go in. The first team goes and inspects, safety inspection, does the safety inspection. And if everything is safe for people to workers to enter, then the clearing of the mud starts with the machineries. Again, after clearing of the mud, the joint team of the experts inspects it. They again decide on the actual support for the location portion blasted just now, and decide the required support for the next excavation. Again, it starts from number 2 and decides for the next drill depth, number of holes, like that. So this is a cycle. So usually in a day, there will be 6, 7, or 8, or even 10 cycles like this, depending on the rock condition, climatic condition, and everything is working fine. It's very quick. This is a pictorial representation of this excavation cycle, which we have seen in the previous slide. This is another way of showing that whatever we do, 13 operations like this. Different figures in different ways, that's all. Now let's see how the tunnel phase is inspected by the experts after a blast. I'll show you how they are. You'll get a feel how these people are going to going inside and inspecting. I hope you got an idea how people go inside and inspect after blasting. So this is how there will be a lot of people. Now you could see only a few people, other people are behind the camera. So this is how they inspect and fill up the REST and ATSS, two forms which I have shown earlier. The supporting system, when you go detail in the supporting system, as I told you, supporting system is for preventing loosening of rope and falling down of small pieces and all those things. So we fish wire mesh around this. Then anchor bolts are fixed. Large, long bolts are driven into this, tightened and fixed with the plate so that loop cross mast is supported. This is one way of it. And if required, we place steel ribs, circular, semicircular shaped steel ribs, which you will see in some of the upcoming photographs, which I am going to show you. Steel ribs are fixed. Then again, shotcrete is done. Shotcrete is done after each stages, mesh, anchor bolts, ribs, as required. Every time shotcrete is done. Then you move forward. After you go working space for the tail end works, so that is about 100 meters or so you move at the face, then the inward flow shower follows it. Then after that, the final concrete lining is given, so the tunnel surface is finished, and then we go for the additional systems like ventilation, electricity, and like that. Of course, temporary ventilation is always given during construction, but once construction is there for the public and everybody, for a completed down, a foolproof, perfect ventilation system has to be provided, also lighting system, communication system, a lot of other things, safety features. So all these things follows. This picture shows drilling, a huge machine drilling hole into the tunnel, and this is a single boom thing. This is 2, 3 boom for 1, 2, 3, 4, 5, 6 booms. So these are all different equipments how we drill inside the tunnel. These are used for drilling holes and driving 4 poles and so many things. So this machinery is working. It's a very interesting. I would like to comment here. In Rohtang Tunnel, when we construct, of course, it's a construction in India. We could see at least 50 to 100 workers working inside the tunnel every day. A team setting these machines, another team filling with explosives, and like that, another team fixing meshes and like that. But when the tunnels constructed in European countries, I visited many tunnel constructions and participated in that one in Austria, Germany, and places. It surprised me. Only less than 10 people do the entire work. The same guys drive this huge machine, comes down, he gets down, takes the other seat, drills the hole, then he moves the machine back, then he and his teammates come and fill up the holes with explosives, they do the wiring, they drive back, blast it. After that, they themselves come inside driving trucks, carry the muck away, like that. It's only 10 people doing the whole work. Anyway, that's a different culture. I just made a comment. So, see, this is the wire mesh. This is the wire mesh, what we fixed. See, here what we have done is that initially before fixing the wire mesh here, some rock bolts are driven into the, because the rocks were loose, so we have driven rock bolts with little plates here, and then did a shotcreting. Then the wire mesh is fixed, and again we will do a shotcreting. This we will do the shotcreting like this. Concrete is pumped, loose concrete is pumped through this machine, and with high pressure, it pushes the concrete like a jet into the face, and it sticks there. This is where the concrete is done. This here you can see the wire mesh, and this will also be covered. This is the steel rip protection. If the rock mass is still worse, the wire mesh and shotcreting and rock bolts is not enough to support this, we will provide steel rips. These are all steel eye sections or channels designed to take the strength of the temporary. It's all temporary support. This is not a permanent support to take care of the entire rock load of the rock mass in the mountain. So all for constructions, but we will not take it out. This will all be embedded behind the concrete line. This is another picture where we show that a rock bolt is seen. It is pushed into, drilled into, and then you can see the plate of the rock bolt. This is where you can see this second shotcrete is done after the wire mesh. A little bit area is given, overlap is given for the overlap of the next concrete. This is another view. Of course, I don't know whether it is night or day because it's just like night. The darkness, 100% darkness, even during noon. This is what we call a rock bolt. This kind of anchors, these are self-drilling. There's a bit at the front. When you turn it, it screws into the rock, and there's a plate here. This plate is not very strong. It will bend when the rock moves or the deflection happens. It has to move. Then only we can measure the strain. So this is a typical rock bolt. This is another type of rock bolt which is called Swellex. We just push in this bolt. So the steel, it is in a curved or wrinkled form inside. Now with high water pump, high pressure water pump, we pump water into it, and with the pressure of this water pump, this swells and fills up this. So that force holds the loose rock. These are all different types of anchor bolts. This is the way the anchor bolt is given. You drive inside and the loose rock mass around it gets supported. As I said, 3D monitoring system. You can read this later when you receive the PowerPoint presentation. Time is running out. So further, so daily basis we monitor this, and we will get an idea about how the deflection is happening, deformation is happening, and then we control it if it is beyond the limit. So the 3D monitoring system measures the stress, strain, displacement, deflection, crack width, geometric deformation, convergence of roof walls. This is what we measure. So these are pictures of the sensors which we fix on the roof. So we collect details from all this. We even use automatic theodolites and manual theodolites also. Not theodolites. Now it is throttle stations. So robotic throttle stations and even manual throttle stations are used to measure this, in addition to the electronic monitoring devices. So this is the output of a monitoring device. Here the deflection is more, and when you come down, deflection lessens and flattens. So that means this is under control. These are the few equipments used for monitoring. These are fixed into the tunnel walls, electronic, and we get the data which is printed out as we saw in the previous slide. as I said earlier, it took about 5-6 months to drill through this distance. 5 years, where we would have taken only 5-6 months to drill through this distance of more than a little bit over half a kilometer. So this took back the project by 5 years. But anyway, the breakthrough occurred in 2017. Breakthrough for students or youngsters, I will tell you, breakthrough tunnel is always constructed from both sides. So here in Rohtang also, we started it from both sides. We started drilling or building the tunnel from the north side, south side, and also from the north side. So from both sides, the tunnel comes in. The alignment is perfectly done because it's not visible, just like building a road or a bridge. So you cannot see the other side. So just by the coordinates and everything, you make it perfect, and then both the sides will exactly, the center line of both sides will exactly meet at one point. If there is a slight error, very, 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 very minute error, 0.0001 error, when you go about 2 kilometers, this will be meters apart, they will never meet. So that will be a total failure. So when this is called breakthrough, when both the ends, drilling from both the ends meet at the center point and tunnel is through at the correct alignment. So actually every tunnel construction, it's a day of big celebration, very, very big celebration. So this happened in October 2017. I'll show you a video about how the leak in Sarinala was. This is how the flow was there. This is after a flow was controlled. Actually, on the first day we couldn't even go there. It was really bad. So this is the flow of water. Even after it is controlled, grouted and everything, and lot of mud, muck and everything like that, you could have seen that. This shows the section of the Sarinala Ridge. This is the tunnel going through. These are all different type of rock masses showing the fault zones. So the geology experts or geology students can look at it at a later time and they can study this. This is the section where the earlier also I've shown this picture, a photograph and drawing about this Sarinala here and the rock faults, rock layers of rock and everything here. This is the tunnel we have here. This is called the interpretive geological cross section. So I have mentioned earlier about the ways we have tackled this Sarinala issue. Again, four-poling, advanced grouting, umbrella roofing, pipe roofing, all these were utilized here to its maximum. And actually, even without blasting, because the soil was so loose like mud or earth, it was not even rock, very, very soft rock, you can call it. Very, very careful excavation, sometimes even manual with spades and pickaxes, sometimes with little bit of excavator machines, and very, very, very controlled blasting mostly. So that is how we proceeded, and this took about 5 years. So this is how the pipe proofing is done, which I have explained earlier. This kind of roof is provided. So what happens is that the span between these two pipes is so less that it will give a support to the entire mass rather than the entire arch span. This is the face where you can see the mud flow. This is something which we have put here to drive grout into these holes. That is advanced grouting. These are all different supporting systems we use during this very, very slow and careful excavation. You see the mud water, slush, everything is shown here, the face. In the earlier photographs, you had seen a very clean face. Here what you see is mud. See, this is the seriousness of it. It is really lucky that no life was lost. Actually, on that day when this happened, I was there in site, not inside the tunnel, but outside in our office. It was really frightening. I cannot even think about it right now. We were all frightened. These are some other photographs, how it looks inside the tunnel. Again, grouting is done through the roof. See, what you have seen in the video, water is flowing out. It's coming like this, side supports are given, a lot of things. All the techniques and technology we can use in tunneling or rock mechanics or any kind of engineering or structural engineering, everything was used. See, these are the German project manager of the contractor. These are our people. They're all there. And the border roads organization people, right from the chief engineer who is a brigadier, right from him down to the engineer, assistant engineer level. All of people were there, full time in the site. I think time is up. I've taken a lot of time, and I'll show you a video which shows a recap of what I have shown earlier. And again, what's inside the tunnel, a little more. The earlier one was about 3 minutes. This is about 6 minutes, and this will give you a good idea about.
सेवा कराई है ना
Sorry.
और क्या सेवा ही हुई होगी बैठ के खाना मिल गया बैठ के चाय मिल गई
Hello.
करती
You
है
can hear a lot of background sounds.
Please unmute. Hello. Please unmute some other
Sir,
sound.
yes, sir. Yes, sir. We have done it, sir. Sorry for the
Okay.
disturbance.
That's okay. I'll go ahead. I'll go ahead. This is the last slide. I think people are getting impatient. So this is the last slide. Just a video. So, thank you very much for listening to me.
It was indeed a pleasure to attend your session, sir. Too much of knowledge was spread throughout the talk. Thank you, sir. Now the platform is open for your doubts, queries. You can make use of your chat box or just unmute yourself for the same. Is there any doubts or queries?
No queries? So let me, as the coordinating person, let me ask a question. Sir, we had had an experience in doing this tunnel in Mecca, Saudi Arabia, but unfortunately, I could not go inside the tunnel because of these problems. Because being an Indian and also a Hindu, they will not permit us to enter into Mecca region. But the design and other things that have been done. So this type of tunneling at that time, we have called it a sprayed concrete lining method. And in that one, the support system we have designed geosynthetics also. Non-woven geotextile were also provided at the top layer, very near to the rock surface. And then with the bolt, we have connected it, followed by a short grating. And there's mesh matting. Then had a second layer of short grate. So such a system has been designed, and I could do only the design part, but I could not see. Now the presentation which I have shown over here is breathtaking, and I can imagine what is the hardships you people have faced. And it is covering almost all part of the civil engineering, that is concreting, soil mechanics, geology, and see here 250-meter above is the Serene Nalla is situated. Especially the Nalla, when we see it is very tricky. This I felt in Oman when I was there, because in Oman there is a lot of hills. So in between the hills there is a loose rock will come, and during rainy season in Oman there will be flood is taking place because this water cannot percolate. Deep, very percolation rate will be slow. That is why flooding occurs in Oman. So in this region also you have that sketches are shown is going, this boulders type of soil is there coming till your tunnel top. That was the reason that the water is coming into inside. And that seepage of water, the movie which you have shown, video, how fast the water is coming and also the quantity of water. Above all those things, the major problem, as an ordinary civil engineer, you can think of. See, it is 800,000 cubic meters of waste you are producing. How we will dispose it of very safely without any environmental impact? That is another headache. But we see that it is very simple issue, but it is one of the major issue you people might have been encountered. 800,000 cubic meters of waste. It's a very fantastic presentation, and it is informative. And I think my chair of the session, Tinu Krishna, as a student, I think he let him say how he felt as a student. Sir, we have student chapters under Trivandrum IGS, Indian Geotechnical Society Trivandrum chapter. We have student chapters.
Yes.
And encouraging our students to come up with this civil engineering and feel them what is civil engineering. It is very challenging. It's not just like reading books and understanding what is bending moment and what is shear force or trying and what is void ratio or porosity. But when you come into actual practice, it is thrill. It is challenging. That is the one which makes a civil engineer more proud. So as a student, let me know his viewpoints. Tinu Krishna, please.
Thank you, sir. Okay. First of all, I would like to thank the speaker, Mr. Engineer Sunil Vasudevan sir, for sharing his valuable time and knowledge with us. And coming to the session, I found this session very useful. Actually, one of the most informative sessions I have ever attended. And regarding presentation, use of photos and videos was very helpful in visualizing the ideas that are being said. And also the methods of tunneling, especially the NAT, the new Australian tunneling method, was very explained very concepts where we were able to understand it very well. And also,
Thank you.
Yeah, also we were aware of the hard work that each and every members of the team were put in this work, especially in the unpredictable situations. Thank you, sir. It was such a really nice presentation.
Thank you very much. I really am a little bit satisfied now that you enjoyed it and you really liked it. So that was my intention for youngsters, students, and young engineers to give an idea about the problems of tunneling and even civil engineering in the work site. You will feel the stress and strain, not like what you study in the book. The bending moment, the stress, strain, everything you can see and feel at the site.
Thank you. Thank you,
very
Tinu
much
Krishna.
for your kind words.
And
Yeah. So
there's
we are
one more
confident
request.
about.
One more request
Yeah.
from my side, Sunil sir.
Yes.
Please permit us to share these videos and your slides also in our future presentations to students.
Sure, absolutely no issues. You can share this video and I will email the entire PowerPoint presentation later tonight or tomorrow morning.
Okay, thank you, sir. Thank you very much.
You can share it, and my phone number and the mail details are also given in that. Anybody having any doubt about my presentation, anything about it, I can give the answers to the limit of my knowledge.
Okay, it's
okay. What you said
Thank
is
you, sir. That was so great of you.
Sorry.
No, yes, sir. Please, sir, you can continue.
No, I was just telling what you had an experience in Oman. This similar kind of experience I had while I was in Dubai. I was in Halcro as a design engineer. I was designing the Corfacan tunnel. So we had a kind of similar problem there. What you explained, I remember it now. But we didn't use any geotextile materials because that was not very common at that time. That was in 1999.
Okay.
Okay.
So this was 2006. My experience was 2006 to 2009.
Okay. That, mine was about 10 years ago. Before that. Okay.
Okay. Thank you, sir.
Thank you.
Back to moderators.
Though we are confident about the brilliant session, still we want the feedback from the participants. So can we have some genuine feedbacks?
Hi, sir. I'm Gopika. Hello.
Yes.
First of all, thank you, sir, for giving such a wonderful session. It was very informative and engaging. I hope all those who heard your talk got many new information about. Thank you, sir, for sharing your knowledge with us. Thank you so much, sir.
Thank you.
Thank you. Anybody else?
Hi, sir. I am Nihara Nair and I am currently pursuing my 7th semester in civil engineering. It was indeed a really eye-opening session for me. Well, it was more or less like a virtual tour to Atal Tunnel. And I'm really thankful to you, sir, for taking up such a interesting and an informative session for us. And of course, seeing all those videos, I'm really sure that all the budding engineers will aspire to be a part of such challenging projects. So thank you so much, sir, for taking up the initiative. Thank you so much, sir.
Thank you.
Thank you. As a small token of appreciation, love, and gratitude on behalf of the entire IGS student chapter, Marine Engineering College, we would like to give you a token of appreciation to the speaker, E.R. Sunil Vasudevan, sir. Can we have the memento on the screen?
Thank you, Sunil sir. Can you please stop sharing so that we can operate, sir?
One second. I'm trying to do that. I'm looking for the button.
Okay, sir. Take your time, sir.
This has gone somewhere. Let me. I can't see this where it's not coming up. I think somebody has taken control or.
No, sir. You're the presenter. You can just stop the sharing.
I got this.
Yeah, sir.
Sorry, we are not so computer savvy old people.
No, sir. It's okay, sir. Really, thank you, sir. I feel proud that at this moment that I contacted you long back, 1 month back, and you're preparing for this for the last 1 month. Took a lot of effort for making the student aware of all the even small things. We got all our overall idea about all the projects. I hope every student and every attendee, even so much of good feedbacks are coming up. So I feel really happy that I made that possible. It was my dream actually to make the Atal Tunnel into this symposium. So that was my personal. What I say, I feel that I feel happy and so much of credit that you are a person in Trivandrum. So it's a credit for College of Engineering Trivandrum also, DKM College also, and for IGS also. At least I got you in the right time, in the right place. So thank you so much, sir, on behalf of the organizer. Thank you, sir. So I'll move on to that. Thank you, sir. I'll move on to that. Thank you, sir, so much, sir. Binu, can you please share? Just 5 minutes, sir.
Sir, is that visible?
Yes. Thank you very much. I'm really honored.
Thank you, sir.
I heard. One second. Let me tell you one thing. I heard some people pronouncing the salutation as E.R. Sunil Vasudevan. That is actually engineer. Architects put it as R, doctors put it as DR. This is engineer Sunil Vasudevan. You should know it. As an engineer, you should know how salutation should be put before an engineer team. Okay, it's just a passing comment. No problems.
Yes. To propose the vote of thanks, I welcome the IGS Student Chapter Vice President and today's co-chair, Tinu Krishna S.
Thank you, Pooja. Good evening. No matter what language you speak, a kind and smiling thank you always speaks to everyone's heart. So, on behalf of the entire IGS Student Chapter, Marine Engineering College, I extend a really hearty vote of thanks to our honorable speaker, Sunil Vasudevan, for a wonderful and informative session. We are really enlightened with your knowledge, and it was really helpful, sir. Thank you, sir.
Thank you very much.
Our sincere gratitude goes to the session chair, Dr. K. Balan, sir, for his support towards this event. Thank you, sir. Also, I extend my sincere thanks to all the dignitaries, faculty members, and students for their valuable participation and support. Last but not the least, I would like to thank our management and all the organizing committee members for their excellent work and effort in making this a success. Thank you all and have a great day.
Thank you, Tinu. Thanking Engineer Sunil Vasudevan, sir, Dr. K. Balan, sir, and all the participants for your cordial and active participation. I hope all our participants have filled the feedback form. If not, do it shortly. We are also expecting your valuable participants for the upcoming symposiums ahead. The next will be on December 3rd, 5 p.m. to 6 p.m. on the topic Road Tunnels General Overview. So with that, we are winding up with this session. This is me, Pooja Ajin, signing off. Thank you.
Pooja, I have to add to that. December 3rd, we have from 6 to 7 p.m. also regarding the engineering design of high-speed rails, both from supported from Arcadis Bombay tomorrow. So please join all for that. I have to add for that. Sorry for that. Thank you. Thank you all for joining. Please fill the feedback form. For all who participated and all who are in the registered list, please do that. Thank you. Thank you, Balan sir, and thank you, Sunil sir, for being with us in the whole time of organizing this. Thank you, one and all.